Hi, in this session we're going to work on a drill problem to get some more practice working with Poisson processes. So remember, a Poisson process is a process that models how things arrive. And the important parameter is lambda, which is the arrival rate, the number of arrivals per unit time. And another important fact to remember for this problem is that when you consider disjoint time intervals, whatever happens in these two disjoint time intervals is independent. So here in this problem, we have trains that are crossing this bridge, and we're told that the trains arrive at this bridge according to a Poisson process at a rate of 3 trains per day. So that doesn't mean that there's exactly 3 trains per day. It just means that in some sense, on average, 3 trains come every day. But the number of trains on each day is actually random. And an important formula to remember is that of a Poisson distribution, which tells you the probability of having k arrivals over a period of tau days. And that's equal to e to the minus lambda tau times lambda tau to the k over k factorial. Okay, so the first part of this problem asks us to find what is the probability that you'll have no trains arriving on days 1, 2, and 3, supposing that there is a train that arrived on day 0. So the information that we're given is that there is a train that arrived on day 0. And then we're asked to find something, a probability related to days 1, 2, and 3. So what we should remember is that disjoint time intervals are independent. So whatever happened on day 0 is independent of what happens on days 1, 2, and 3. So we can actually just forget about the fact that a train arrived on day 0 and just focus on what happens on days 1, 2, and 3. So what we really want is just what's the probability of 0 trains in 3 days. Right? Days 1, 2, and 3 cover 3 days. And if we just now apply this formula, we can know exactly how to find that. So now k is 0, tau is 3, and lambda is 3, given by the problem. So what we get is e to the minus lambda tau. Lambda is 3, tau is 3, so that's e to the minus 9 times lambda tau is 9 to the k, which is 0, over 0 factorial. Right? So 9 to the 0 is 1, 0 factorial is 1. So all you're left with is just e to the minus 9. And that is the probability of having no trains in 3 days. So just remember that destroying time intervals are independent and don't get tripped up over information that actually is irrelevant. Now, part B, we're asked to find what is the probability that if a train arrives on day 0, that it takes more than 3 days for the next train to arrive. Well, if you think about that, really it's asking the exact same thing as part A, because the event that the next train takes more than 3 days is exactly the same as there being no trains in the next 3 days. So in fact, this is exactly equal to the same probability that we calculated in part A, e to the minus 9. All right. Part C now says, what's the probability that you have no trains on days 1 and 2, the first 2 days, but 4 trains on the 4th day? Okay, so now this question involves days 1 and 2 and day 4. So again, let's rely on this fact that disjoint time intervals are independent. So we can actually calculate the probability of no trains in the first 2 days and then calculate the probability of 4 trains on the 4th day and combine them because they're independent. So the probability that we're looking for is 0 trains in days 1 and 2 and 4 trains on day 4. Okay. But because this is independent, we can actually calculate the probability of this first part, the probability of the second part, and multiply them together. So what's the probability of no trains in days 1 and 2? Well, that is just, again, probability of no arrivals in a duration of length 2, which, again, we can calculate using this formula, where k is 0 and tau is now 2. So what we get is e to the minus lambda tau. Lambda tau here is minus 6. 6 times 6 to the 0 over 0 factorial. So that's the first part, the probability of 0 trains in days 1 and 2. Now, what's the probability of 4 trains in day 4? Well, we want now the probability of 4 arrivals in a duration of length 1, which we can, again, use this formula to calculate. That's going to be e to the minus lambda tau. Now tau is 1, and k we want to be equal to 4. So lambda tau is 3, and we want lambda tau 3 to the 4th over 4 factorial. And now that is just going to be equal to, we can pull out an e to the minus 9 here. This 6 to the 0 over 0 factorial is just 1. And then the rest of it is just times 3 to the 4th over 4 factorial, which we can actually could simplify it if we wanted to. OK. So again, that relied on this fact that the disjoint time intervals are independent. And that's an important tool to have. The next and last part of this problem asks us for the probability that it'll take more than 2 days for the 5th train to arrive. So we want the probability that more than 2 days for 5th train. OK. Well, what's another way of saying that? In order to take more than 2 days for the 5th train to arrive, that's exactly the same as saying there was no more than 4 trains in the first 2 days, right? So we've transformed this into something about the number of days until a certain arrival to the number of arrivals within a certain number of days. Because if you have no more than 4 trains in the first 2 days, then automatically you need the 5th train could not have arrived until after 2 days. Now, there's obviously you can calculate using either of these. In this way, you would have to calculate something. You would have to know something about the distribution of the 5th arrival time and calculate whether or not that's the probability of that being greater than 2, which you could do. Alternatively, you could also reframe it in terms of the probability of having no more than a certain number of arrivals within the first 2 days. So let's do it in this case using the second method. We want now the probability of no more than 4 trains in the first 2 days. Well, that's the same as the probability of there being 0 trains in the first 2 days, plus the probability of being 1 train, and so on, all the way up to 4 trains, right? Because you can't have both 1 train in the first 2 days and 2 trains in the first 2 days. So those probabilities you can just add up. And so it turns out that it's just equal to the probability of the sum for k equals 0 up to 4 of the probability of having exactly k arrivals in 2 days. So probability of having k arrivals in 2 days is just e to the minus lambda tau. Lambda is 3 still. Tau is 2 now, so it's e to the minus 6 times 6 to the k over k factorial. And now we can simplify this somewhat and actually calculate out what this summation equals. We pull out an e to the minus 6. Then we get 6 to the 0 over 0 factorial plus 6 to the first power over 1 factorial plus all the way to 6 to the 4th over 4 factorial. And now the last part is we can actually calculate out what that number is equal to. And it turns out it's equal to 115 times e to the minus 6. OK. So this last problem just demonstrates that there's multiple ways of framing any particular problem. You can frame it in terms of arrival times, or you can frame it in terms of the number of arrivals. And depending on the situation, maybe one way is easier than the other one. OK, so that was just a quick drill problem for Poisson processes. And I hope that was helpful. And see you next time.